Hello, everyone. Welcome to pre-lecture 14. We're going to go into some ways we do calculations around acids and bases in this pre-lecture. So let's see if I can get this to go forward here. So just a reminder from last class, we talked about how we can determine pH and POH, as well as go between pH, POH, and our concentration of hydronium and our concentration of hydroxide in our solution. Reminder, key way to do that is using Kw here, where our concentration of hydronium times our concentration of hydroxide is equal to 1 times 10 to the negative 14. Okay. Also a reminder, these are going to be our strong acids and bases for this semester. Memorize this if you have to. And then we also have weak acids and bases. And in particular, last class, we talked about weak acids with general example shown here where we have some weak acid dissociating into H plus and A minus, which is just general base. We would, of course, then calculate our equilibrium constant Ka by doing our products over our reactants raised to their powers. Okay. Something that we didn't talk about last class that we'll get into is we have strong and weak acids. We also have concentrated acids and dilute acids. And so concentrated acids are anything or bases are anything we would say that has a greater than 1 molar concentration. They can still be very dangerous to work with, even if they're weak acids. If we contrast that with dilute acids and bases, they have a low concentration. Generally, they're dilute enough to not be harmful. And so even if we have a strong acid, if it's dilute and it's close to a neutral pH, then it would be perfectly safe to work with, right? So just to give you kind of an idea of different strengths of different acids and bases, we have this nice chart from our textbook where we get our strongest acids up here. Again, these are all the ones on our list. And after that, we get our hydronium ion, and then these are the next strongest acids going down this way. And we also then have our bases. And so something to notice here is that everything across each row is going to be a conjugate. And so the stronger our acid, for example, perchloric acid up here, is then our weakest base. And so generally speaking, not generally speaking, all the time speaking, the stronger our acid is, the weaker its conjugate base. So for example, methane would then be our weakest acid, but it will be the strongest conjugate base. Okay, then everything else is in between, obviously. So something like acetic acid that we're going to talk about a little bit later in this pre-lecture is a weak acid, but it's kind of in the middle. And because of that, it will form a weak base, or at least a decently strong base as a conjugate. Okay. So we've talked about weak acids. This is their general formula. We also have weak bases. And so with weak bases, for their ionization or their generally how they react with water or in water, weak bases tend not to dissociate, but they tend to react with water in order to produce some sort of conjugate acid. So again, if we have a base reacting with water, our base is going to be our base. Water is going to act as our acid, to where then our conjugate acid is this Hb plus, and our conjugate base is going to be hydroxide. And if we were to write out this equation, instead of calculating Ka, we would calculate Kb. And Kb will give us, again, products over reactants. Okay. As Ka gets larger, the strength of our acid increases. As Kb gets larger, the strength of our base increases. And of course, that makes sense because as we think about our products over our reactants, the more products we get, the bigger our K values are going to get. And so that is a direct reflection of the strength of our acids or bases. Just so you know, for strong acids and bases, Ka and Kb is about infinity. That's because they fully dissociate, right? So we have no reactants left. Okay. And so if we think about our relative acid strength, this is how we would kind of judge that. So our Ka of 1 is very strong, obviously then. And as we get more negative with our exponents, those are going to be weaker and weaker acids, all the way down to water being quite a weak acid. We then again can look to our conjugate bases. So the stronger the acid, the weaker our conjugate base. So this is essentially just reversed from the other direction, right? Okay. One other concept that I'll talk about in this pre-lecture is percent ionization. This is another way we can calculate how much something dissociates. And so all it is the concentration of our hydronium divided by the concentration of our weak acid times 100. If we have an acid, if we have a base, it'll be the concentration of our hydroxide divided by the concentration of the base times 100. So pretty simple formula, kind of like percent error, but just measuring how much things ionize. And of course, to keep that straight, H3O plus is an ion, OH minus is an ion. That's how we can remember it. Measuring percent ionization. Okay. All right, so one example that I want to do as part of this pre-lecture video is talk about acetic acid being that's the principal part of vinegar. So when you've had anything with vinegar in it, which I'm sure you all have, is about a 3% vinegar solution. And so at a solution that is at equilibrium has the following concentrations of the chemical formula for acetic acid. We have hydronium, H3O plus. That concentration is equal to our conjugate base, which is an anion, which hopefully you remember from Gen Chem 1 called acetate. And then those have the same concentration. And I ask you, what is the value for Ka for acetic acid? So with these equilibrium problems, would highly recommend doing two things, starting by writing out your chemical equation and then your Ka expression. And so our chemical equation, if we think of that, is going to be CH3CO2H. That's going to be aqueous. That's our acetic acid. And then that is going to be an equilibrium, or rather, sorry, let me get ahead of myself, because in this situation, we have hydronium that's going to need to react with water, right? So H2O as a liquid being present, and that will balance our chemical equation, where we then go in equilibrium between our reactants. One of our products will be our hydronium, H3O plus, be soluble. And then we also end up with acetate, CH3CO2 minus. That'll be aqueous as well. Okay, so that is our equilibrium, or that is our chemical equation. Our equilibrium expression can then be Ka, because acid, definitely an acid. It's going to be equal to our products over our reactants raised to their powers. And so H3O plus CH3CO2 minus. Oops, minus didn't really show up. And we divide that just by CH3CO2H, our acetic acid, right? We wouldn't include water because it is a pure liquid. And so we don't count that in our equilibrium expression. That's our Ka expression. We might be thinking to ourselves, do we need to do an ice chart here? And the answer is we don't. And the reason that we don't is because if we reread our question, hopefully we see that it contains the clause at equilibrium. So we know that when we're at equilibrium, those are going to be our concentrations, meaning we can jump right into plugging things into our equilibrium expression. So I will do that. Ka is going to be equal to 0.00118, and I'm just going to square that because it is both the concentration of our H3O plus and our acetate minus. So I'm going to square that, and then that is divided by our acetic acid concentration of 0.0787. So if we do the math there, I got a value of 1.77 times 10 to the negative 5. And just a reminder that any K, equilibrium K that we calculate is going to be unitless. And so that would be our final answer there. Okay. Hope that was helpful for that problem in calculating K. We will be doing some examples where we'll need to use ice charts in class. So just clear those, and then we can say that is it for this pre-lecture. If you have any questions, please let me know. Otherwise, I will see you in class.